All right, welcome ladies and gentlemen. This is video number 7 for our atomic theory unit. Once again, you're going to need your note packet open to where it says video number 7, and you will also need your periodic table and your reference table for this particular video. This video is about excited state electron configuration. So now that we've already talked about ground state, excited state, what happens in terms of energy, we can now look at how the electron configuration will be changed, because our goal is to be able to recognize if we have an excited state electron configuration or not and relate that to the atoms. So first of all, it is entirely possible to tell simply from an electron configuration if the atoms have electrons in the excited state or not. Remember, excited state is when the electron moves to a higher energy shell, one where it doesn't usually belong, and this leaves an empty position open at a lower energy shell. And that's exactly what we look for to determine if an electron, if an electron configuration is in an excited state. If an energy level is not completely full, but the next shell up has electrons in it, meaning if everything, if you never look at your outermost shell, you only look at everything up to the outermost shell. If there's an open position in one of those shells, then you know you have an excited state configuration. It basically means that that open position at a lower energy shell, that one of the electrons that's at the highest energy shell shouldn't be there. It doesn't belong there. It's an excited state electron, and ultimately it's going to return to that open position at the lower energy shell. So that's what we're looking for. We're looking for an open position at a lower energy shell. So we have to remember how many electrons fit per shell. So remember 2 in the first shell, 8 in the second, 18 in the third, so on and so forth. That way you know, is there an open position? Is the shell full or not? So just as an example, 2-8-8, this is not an excited state configuration. The reason I know that it's not excited state is, first of all, I don't look at the last one, but I look at everything that comes before it. In the first shell, it can only fit 2 electrons, and it has 2 electrons, so that's full. The second shell can only fit 8 electrons, and it has 8 electrons, so that is also full. So this is not an excited state. This is a ground state configuration. But 2-7-8, this is an excited state configuration. Again, I don't look at the last shell, but I look at everything that comes before it. The first shell has 2 electrons, so that's full. But that second shell, notice this arrow right here, it's not full. I can fit 1 more electron in the second shell. So it means that one of the electrons here is excited, and it doesn't actually belong in the third shell. And ultimately that excited electron is going to return to the second shell, to that open position in the second shell, and give off light in that process of doing that. So 2-7-8 is an excited state electron configuration. You can fit more electrons in that second shell, but you still have electrons in the third shell. So one of those electrons in the third shell is an excited electron. It's going to return to the second shell. Now, a comment about this, and this is a really huge thing, so I want you to open up your periodic table. All of the electron configurations that are on your periodic table are ground state. So I want you to write in, like on the side or something somewhere on your periodic table, ground state electron configurations. Now I bring this up because if you look, for example, at calcium, its electron configuration is 2-8-8-2. Now, this is actually a ground state configuration, even though you might be saying, but Mrs. Julian, you literally just told me that if you have an unfilled previous shell, but electrons higher up, that means it's excited. In the third shell, and I know this because I was paying attention, third shell can fit 18 electrons. And yes, I agree with you. However, all the electron configurations on your periodic table are in fact ground state. So why do we have this situation? Bohr was wrong. That's why we have this situation. Your electron configurations are based on the Bohr model, and Bohr was wrong. Bohr was not correct. So his idea of just having energy shells is actually not completely correct, which is why I don't really like electron configurations that are just based on energy shells, because you get into this particular situation. So just know that there is actually more to it than just what Bohr said. And when we look at the existence of something called subshells, which is in the next model, then that kind of starts to explain why you have the situation with calcium, why the third shell is not completely full, but we've actually started putting electrons in the fourth shell. These are all ground state configurations. That's the only takeaway that you need. These are in fact ground state electron configurations, and the reason why it doesn't make sense is because Bohr was wrong, and these are based on Bohr's model. So we're going to do a bit of a practice with this just to show you my point. Which of these are ground state and which are excited state? Atoms And we want to know, basically we want to practice identifying the atoms. So this first one, 1-1, first of all, this is an excited state because the first one isn't full. Again, we never look at the last one, but we look at the first one. The first one isn't full, but there are electrons in the second shell, so this is an excited state. But what is it an excited state atom of? Well, there are 2 electrons here, which means that there also must be 2 protons here. So if there's 2 protons, there's only one element that can be, and that's helium. So this first one represents an excited state electron configuration for a helium atom. The next one is 2-6. This is a ground state configuration because, again, we never look at the last one, so the last one doesn't matter, and the first one is full. So that means it's ground state. Everything up to the last one is full. But again, we want to figure out what atom it is. So this is 2-6, which means there's a total of 8 electrons, which if it's an atom means that there are also 8 protons. And if there's 8 protons, that means it's oxygen. So this is the ground state electron configuration for oxygen. 2-8-2. Don't look at the last one. This is full, so that makes it ground state. 12 electrons mean 12 protons, and the only element that has 12 protons is magnesium, so this is a ground state configuration for magnesium. 2-7-3, however, again, don't look at the last one for excited state. This is full, but 7 is incomplete, which means that there's an electron that belongs there that is actually in the third shell. So this is an excited state configuration, but we still have the 12 electrons, so now this is an excited state configuration for magnesium. So we have the ground state for magnesium and then the excited state for magnesium. 1-7 is an excited state because this first one is incomplete. That's what you look for. And it's 8 electrons, which means it's 8 protons. So now this is an excited state configuration for oxygen. 2-7, however, this is ground state. Because again, the 7 at the end, it doesn't really matter, but it's everything that comes before it. This is full. The first shell is full. So that this is a ground state configuration. This is 9 electrons, so we must have 9 protons. So this is a ground state configuration for fluorine. So the final thing on this, if you're asked to write an excited state electron configuration for an atom, there are 2 things that you have to do. The first thing that you have to do is ensure that you have the correct number of electrons for a given element, and that's based on the number of protons, because again, in an atom, the number of protons is equal to the number of electrons. So if it's, let's say silicon has got 14 electrons. You best make sure that you've got 14 electrons in your electron configuration. If you have any more or any less, it's not correct because you don't have the correct atom. And then the next thing you want to do if you're writing an excited state configuration is to ensure that it is in fact an excited state, i.e. move at least 1 electron up to a higher energy shell than it exists in the ground state, and use your periodic table to get the ground state configuration and then simply make it an excited state configuration. So for example, a perfectly valid test question would be write an excited state electron configuration for phosphorus. So let's start by looking up the ground state configuration for phosphorus. So that's just right off of your periodic table, and you look it up, and it's 2-8-5. Now there's a total of 15 electrons in this configuration, so we need to maintain this. So this is ground. That's not our answer because we want excited state. So what you want to do is alter this configuration by moving an electron, moving at least 1 electron up to a higher energy shell. There are truly thousands of ways that you can do this with these 15 electrons. So I'm going to give you lots of examples. 2-8-5. You could take one from the second shell and move it up to the third shell. So you could do 2-7-6, right? Pushing that second one in the second shell up to the third shell. You could take one that's in the third shell and push it to the fourth shell. You can do that. You can add on shells because those shells are really there. It's just they're unoccupied. So I could also say 2-8-4-1. You could take something from the first shell and bump it up to the third shell. They can skip shells. They don't have to go just 1 shell at a time. They can actually jump multiple shells at a time. So I could do, not 2, I could do 1-8-6. That would work. That would absolutely work. You could do 2 electrons. You could move more than 1 electron. You could do, 1-7 and then put everything else there. I hope you're kind of getting the idea that there are lots of ways to do this, and I am by no means covering all of them. So when I grade a question like this, I'm really grading it in 2 aspects, because not everyone's going to have the same answer. And the 2 aspects are right here. Number 1, do you have the correct number of electrons? If it's phosphorus, it has to have 15 electrons. If you don't have 15 electrons, it's not phosphorus, not an atom of phosphorus. And number 2, is it an excited state configuration? Meaning, is it not ground? Meaning, this is not an acceptable answer, but literally almost any other possible configuration for phosphorus would be an acceptable answer. So we're going to practice again a little bit more with recognizing excited electron configurations, and then writing some excited state electron configurations.